Hi everybody, I'm Greg Fishel and welcome to bonus weather video number 1 for this week. And we've talked before about spin in the atmosphere, the scientific term for it being vorticity, and that there were a couple of ways to bring that about. Number 1 was curvature of the flow. Number 2 was the amount of wind shear over a given distance, okay? But wait, there's a third way, and that's what we're going to talk about today. So just a little bit of review. Vorticity is defined as being the measure of rotation in a fluid. Now, you may not think of the air as being a fluid, but in scientific terms it is. It's just a different type of fluid than, say, the ocean or a river or something like that. One factor is the curvature of the flow. So if the flow curves a lot, then you have vorticity, either positive or negative. Another factor is the wind shear, how much the wind speed changes over a given horizontal distance. And it is the advection, or the movement of vorticity, that leads to upward and downward motion in the atmosphere. So if you're sitting in a place that has relatively low values, but the flow pattern is advecting or moving higher values toward you, then you would be in positive vorticity advection, and that would lead to upward motion. If lower values are upstream and they're moving in your direction, that's negative vorticity advection, and that typically leads to sinking motion in the atmosphere. Now here's a way to look at this pictorially. So this is a flow that is curved, and the greatest curvature is right in here. So just based on this alone, you would expect the vorticity maximum to be maybe about here. Then there's wind shear. So let's supposing we have a westerly flow, and the strongest winds are in here, and then it drops off both to the north and to the south. And we're going to put a couple of blocks of wood in the way of that flow just to see how they're affected by these changes of wind. Now, again, you're sort of looking down here, okay, from above, and so we're not talking about the wind changing with height. We're talking about it changing horizontally along the whatever surface you're at. It could be the surface, it could be 500 millibars, whatever, but we're looking at horizontal wind shear here, okay? Just want to make that clear. So, because the winds are blowing more strongly on this part of the block of wood than it is up here, then that means that block of wood is going to start to rotate in a counterclockwise manner, or cyclonically. Now, this block of wood, you actually have stronger winds at the top than at the bottom, and so it starts to rotate in a clockwise manner, or anticyclonically. So this horizontal wind shear is creating both positive and negative vorticity, if you will, just by nature of the change in wind speed over a given distance. But what about something we call planetary vorticity? Well, by nature of its rotation, the Earth actually imparts vorticity to the air above it. The equation for that is 2 times omega times the sine of your latitude. Now, omega is simply a Greek letter, as you know, and it is the speed at which the Earth rotates, okay? And planetary vorticity then, because of this equation, the sine of the latitude, is very dependent on the latitude. And the one thing I want you to think about here, and I get tongue-tied when I try to explain this, but you know, the Earth is obviously rotating at the same speed everywhere, but it's an angular speed, okay? If you look at the actual distance that is covered by the air, or the Earth, if you will, at the equator, it's a bigger distance than it is anywhere else on the Earth because the circumference of the Earth is widest at the equator, and then it gradually narrows as you go toward the North Pole. So more ground has to be covered in order to make one complete rotation at the equator than it does anywhere else on the Earth. And so that, in a sense, is what causes this cyclonic vorticity, or counterclockwise vorticity, to be generated by the Earth's rotation itself. So here's a table showing the values here by latitude. And by the way, if you have a degree in meteorology or you know something about this, the units are technically this number times 10 to the minus 5, which means you move the decimal point back 5 places, okay? There's no weather map in the world that labels vorticity like that. They just leave off the exponent and they take the value in front of it. And so that's what we're doing here. So at the equator, there is no planetary vorticity at all, okay? But as you head north and south, then you start to generate it. And by the time you get to 30 degrees north latitude, it's about 7 units. And if you get up toward New York City, about 9. Around Caribou, Maine, 11. And then up at the North Pole, it's 14. So again, the farther north you go, the more the Earth's rotation is helping out in the sense of it's generating cyclonic vorticity, which is the kind of vorticity that is going to lead to storms and so forth. Of course, if you're not a storm lover, then you don't want that. All right, couple more definitions. Relative vorticity is the spin created by the flow itself, either the curvature or the wind shear. Planetary vorticity is the spin created by the Earth's rotation, and absolute vorticity is the sum of the relative vorticity and the planetary vorticity. And as I was putting this presentation together and talking so much about spin, I couldn't help but think of my good friend Tom Campbell, who used to produce a show called NC Spin. It was basically a show where people with different political perspectives were giving their views on a given issue, and he was the moderator to make sure that everybody stayed civil. And I've known Tom a long time. He's just a wonderful, wonderful guy, and he's a fixture in North Carolina. And so I thought of him when I was doing all this talking about spin. So, Tom, I hope you're doing okay, and we'll make sure we catch up soon. All right, so here's an example of a weather map. And notice here over on the left, the legend, there are no colors before you get to about 16. So 16 is a pretty healthy value of vorticity, one you might associate with a well-developed system. Now, notice the vorticity maximum. I don't know if you can see the X right there, is right here. But notice how the greatest curvature of the flow is back here. And so you're sitting there thinking, well, why is this thing up here? Okay, good reason. You notice how all these lines, and think of these lines as being isobars in the upper atmosphere. You notice how they're most tightly packed right in here? So the drop-off from these strongest winds here to lighter winds here is greatest at this location. And so that's why the vorticity maximum is located where it is. It's more related to wind shear in this case. Now, you do notice that it does extend back toward that area of curvature, but the maximum value itself is actually up here. Okay. So in conclusion, there are lots of ways to make the air spin. The farther north you go in the northern hemisphere, the more the Earth helps out with cyclonic rotation. So the same system at, say, 30 degrees north latitude, just looking at the system itself, don't take into account the Earth's rotation at all. You take that system and put it 30 degrees farther north, and the Earth is going to make it an even stronger system, okay? So no question that the farther north you go, the more the Earth helps out with storms. And it's the advection, or the movement of positive vorticity, that causes upward motion in the atmosphere. As I talked before, that if you're in an area with low values, but the flow is moving higher values toward you, that is called positive vorticity advection, and typically it makes the air go up. And that leads to clouds and precipitation, if there's enough moisture present. Okay. I hope that made a little bit of sense. Hope there wasn't too much spin in this presentation. We'll have another bonus weather video for you coming up on Friday, and another daily weather update coming up later this afternoon. So we hope to see you for both of those, or at least one of them. And we'll talk to you soon. Have a great Tuesday.